Alrighty, let's talk about balancing equations. This is a skill that you're going to learn here and then use it for the entire rest of the year. It's something that we'll do in every unit from here on out, so it's really important to get on board quick and be comfortable with this as soon as you can. So balancing chemical equations, just as a reminder, chemical equation looks like this. It's basically just sort of an outline for what will happen when elements and compounds react together and what it is that they'll make and that sort of stuff. So remember that on the left side here we have our reactants, and then over here we have our product. So this is just a simple synthesis reaction of sodium and chlorine gas to make sodium chloride. There's a problem with that equation, though, and we'll talk about it. The idea of balancing equations has to do with preserving the law of conservation of mass. And that's something you may have heard about in your physical science class, and we use it a ton here in chemistry. And basically, here, what we want to make sure that we adhere to is that every reactant atom is also present as a product atom. So every reactant has to be accounted for as a product. And in our last equation, we had a little bit of an issue. So here is that equation again. Sodium and chlorine gas gives us sodium chloride. And if you look at it from more of a graphic standpoint, you might think of these little circles as being the atoms that are making up these things. So a sodium and two chlorines makes sodium chloride. Probably what you see right off the bat is that the sodium atom is accounted for. There's one of them over here and one of them over here, but the chlorines, we somehow lose one in the process, and that is what we mean by preserving the conservation of mass. We've got to account for that second chlorine atom somehow, and you can't just simply say, well, we're going to make sodium chloride, and chlorine atom or something like that. That's not what the equation states. So you can't just go throwing it in there. So we got to figure out a way to account for that other chloride ion. And it's pretty easy. In our class, we use something called the bookkeeping method. And it's just a way of adding coefficient numbers which would exist at the front of the symbols. You can't ever insert anything into the middle of a compound. You can't put a coefficient number between two symbols, and you certainly can't adjust the subscripts or anything like that, or add subscripts, because that changes the nature of the chemical compound. So the only thing we can do to balance these things out is to add numbers that will distribute by multiplication to the subscripts that are present in the formulas. Okay, so the way that this goes is as follows. You want to underline the reaction and then divide it under that arrow. That separates the reactant side from the product side, and then list out by element the things that are present. We have iron and oxygen, and make sure you don't list, we don't bring the subscripts down with the elemental symbols, just the elemental symbols, Fe and O. Duplicate your list on the product side as well, and then we're going to take what we call the initial count of our unbalanced reaction here to determine how many atoms of each element there are. That'll help us see how we're going to fix this thing. So this is where you would look at any subscripts. Remember, there's a little imaginary 1 right there, which means there's 1 iron atom. Here, it's a 2 for the oxygen. Over here, the iron, we have 2 of them, and the oxygen, we have 3. So this is a big problem because a product just can't have more atoms than we started with. This reaction is all kinds of unbalanced, so we have to put in some work to fix this. So the way we do it is with coefficients. We want to make the numbers of each atom the same. So we can double the number of irons over here by adding a 2 coefficient, and that will change just the iron count from 1 to 2. We've basically multiplied the 2 by the 1, right? So irons are fixed, irons are good. Oxygens, we have a little bit harder situation because we can't just double one side to equal the other. When you're in a situation where you have like a 2 and a 3 or something like that, you want to shoot for the lowest common multiple, which in this case is a 6. And so to make the 3 into a 6, we have to double the number of oxygen atoms, right? So oxygen, that 2, again, remember, that multiplies by the 3 to make a 6, but it also multiplies by the 2, which changes our iron count to 4. Okay, we'll come back to iron here in a second. Oxygen over here is a pretty easy fix to match that 6. We would just triple it, and that makes for 6. Now, as what happens a lot of times is that you will solve one problem and create another, like we did with our irons here. It was fine at 2, and then we made this change that made it out of balance again. So over here, we can change the coefficient that we started with from a 2 to a 4, and then that would just make this counted up number of irons into a 4. So now we can see that we've got a balanced equation with a coefficient 4, 3, and 2, and that makes everything balanced. So you'll notice that the irons are 4 and the oxygens are 6. That's fine. You don't need them all to be the same number. You just need, each individual atom to be represented in the same way on both sides. Okay, so here's a little trickier one. This guy right here. I've already started this one for us. This one looks a little bit harder because we've got a lot more, not a lot more, but we've got more elements to take into account. We've got nitrogen, hydrogen, sulfur, barium, and oxygen. And when you have these elements that exist in multiple compounds, like the nitrogen is in the ammonium and it's also in the nitrate, that makes for pretty challenging balancing. But there is a shortcut here, and that is that if the polyatomic ions exist on both sides of the arrow and they haven't come apart from each other in any way, like NH4 on the left and NH4 on the right, that's a good situation, because then you can use the formula for the polyatomic ion instead of separating out the elements, which actually makes things quite a bit easier. So we can see here that our ammonium hasn't come apart, our sulfate hasn't come apart, and neither has the nitrate. So that makes life quite a bit easier. We actually like to see polyatomic ions in these formulas. So let's take our initial count of these things. Remember, that little 2 subscript is only applied to the ammonium. The sulfate we only have 1 of, and please don't mistake that 4 for being the number of sulfates. That 4 is just part of the formula for the sulfate ion, so that's just something that hopefully we're familiar with by now. Barium we have 1, and nitrate we have 2. Over here we got a 1, sulfate is also a 1, barium's a 1, and yeah, nitrate's also a 1. Okay, so this isn't too badly out of whack. We can make some quick changes here. Let's change our ammonium number to a 2. That also changes the nitrate to a 2. There we go. So this can happen too. When you fix one problem, you just inadvertently fix another problem, and that's what happened here. So all that this one took to balance was just that coefficient of 2 in front of this formula right here. So pretty easy stuff. So I think if I were gonna outline the way that this should go from a procedural standpoint, I would just follow these steps. Underline the reaction, divide it up with the line, list out the elements that are present, or the polyatomic ions if they're present, count up the atoms in that initial count, and then use coefficient numbers to balance reactants with products. Okay, it's pretty easy. Now you can see though that if you write your formula incorrectly, then balancing an equation is really close to impossible. Like let's say that you were going to put your ammonium together with your sulfate somehow, and let's say that you forgot that subscript 2, then your count would be wrong, and then none of the coefficients would really work, and it's just a mess. So the idea is to get very good at putting these formulas together so that your equation is written right, and that allows you to balance it easily and correctly. Okay, so that's balancing equations for you.